Okay. Good morning. From today on, we're going to have a look at chapter 2 of this course, which is more about the derivatives. So today we're going to have a look at the derivative rules, part 1, which are simple derivative rules. Tomorrow we'll have a look at more complex derivative rules. First, let's have a look at today's learning goals. After this lesson, you are expected to first understand common derivative rules, including constant rule, power rule, constant multiple rule, sum rule, difference rule, product rule, and quotient rule. Actually, most of these simple rules are quite intuitive. Apply the common derivative rules to solve related problems and differentiate a polynomial function. Last, differentiate a rational function. Okay, so let's have a look at these common derivative rules. First, let's give it a quick recap of the rules we have already learned. So in chapter 1, we have learned the constant rule and power rule, right? This constant rule states that if we let c be a constant, then fx equals c is a constant function, right? Then we'll have the derivative of a constant function is 0. Derivative of a constant function is 0, which means instantaneous rate of change is 0 everywhere. Okay, power rule states that if fx equals x to the power of n, where n is any real number, then the derivative of fx, f prime x, equals n times x to the power of n minus 1, or df by dx equals n times x to the power of x n minus 1. Can you recall this? Okay, so these are the two rules we have already learned, okay? Then, from today on, we'll increasingly add more rules to the derivatives. Okay, first of all, let's have a look at the next rule, which is called the constant multiple rule, which basically means we can put the two rules, what we have learned here, together. So the constant multiple rule states that if c is a constant and gx is differentiable function, then fx equals c times gx, then we can find the derivative of fx at any point x equals c times the derivative of gx. Or you can also express that using the Leibniz notation, which means df by dx equals c times gx by dx, which equals c times dgx by dx. Any questions? So now ask yourself a question. Can you prove this theorem here? Can you prove this theorem is true? I'll give you 2 minutes to think about that. Okay, all right, let's have a look at the proof here. So actually you can prove this using the first principle definition. The derivative of fx is the limit of x, fx plus h minus fx over h1, h approaches 0, right? Then let's put all values in. Fx plus h is just c times gx plus h. And fx is c times gx, right? Then we can put c in front. C is a common factor. So that's limit of c times the ratio between the difference of g of x plus h minus gx over h. And the limit of c times something, c is a constant, then c can be put in front. This is according to the limit property, right? So that becomes c times the limit of gx plus h minus gx over h when h approaches 0. So that's actually the derivative of gx at any point x. Therefore, that equals c times the derivative gx, right? Therefore, we have proved f prime x equals c times g prime x. Any questions? Okay, so basically we can prove this theorem using the first principle definition, right? Okay, next, let's have a look at example. Find the derivative of each of the following functions. I'll give you 2 minutes, okay? They are very basic examples. Have we finished? Okay, let's see the solutions here. Okay, so according to the constant multiple rule, the first question, the derivative of fx equals 5 times 3 times x to the power of 2, right? First, we can put the constant in front and find the derivative of x cubed. The derivative of x cubed is 3 times x to the power of 2. Therefore, the derivative of fx equals 15 times x squared. Second question, the derivative of fx equals d3x to the power of -1 over 2 by dx. Then we can put the constant 3 in front. Find the derivative of a power function, x to the power of -1 over 2, which is 3 times -1/2 times x to the power of -3 over 2, which can be simplified to -3 over 2x to the power of 3 over 2. Any questions? Okay, if you have no questions, let's have a look at the next rule. Next rule is called the sum rule. This rule states that if fx and gx are both differentiable functions, a new function rx is defined as the sum of fx and gx. Then we have the following rules. The derivative of rx, r prime x, equals the derivative of fx plus the derivative of gx. Or in Lebanese notation, drx by dx equals dfx plus gx by dx, which is simplified to dfx by dx plus dgx by dx. So basically, it means the sum of the derivative of the sum of the two functions equals the sum of the two derivatives. Okay, again, I'll give you 2 minutes to think about how we can prove this rule here. Okay, can you prove this? Okay, let's have a look at the proof here. So if you want to find the derivative of Rx, again, we can use the first principle rule, right? The derivative of Rx is defined as the limit of Rx plus h minus Rx over h as h approaches 0. Then we can substitute Rx plus h by fx plus h plus gx plus h. Then substitute Rx by fx plus gx. Then the denominator is still h, unchanged. So we evaluate this limit as h approaches 0. This expression can be transformed to the limit of first the fx plus h minus fx over h, and the later part is becomes gx plus h minus gx over h. So note here, according to the limit property, the limit of the sum of two functions equals the limit of the first function plus the limit of the second function, right? So note here, the limit of the first function, by definition, is just the derivative of fx. And the limit of the second function is just the derivative of gx. Therefore, we have proved the derivative of Rx equals the derivative of fx and derivative of gx. Therefore, we say, according to the sum rule, the derivative of a sum of two functions equals the sum of the two derivatives. And similarly, we have the next rule, which is called the difference rule. Simply, if you can substitute the plus sign to the minus sign, this is also true. If fx and gx are both differentiable functions, and hx is defined as fx minus gx, then we have the following difference rule. The derivative of hx equals the derivative of fx minus the derivative of gx. Because we have already proved the sum rule, can you prove the difference rule based on the sum rule? This seems a lot much more easier, right? We can prove this by using the sum rule. Because we have the sum rule, which states that the derivative of the sum of two functions equals the sum of the two derivatives of the two functions. Because hx is fx minus gx, which can be written as fx plus minus gx, right? Then we have the derivative of hx, according to the sum rule, equals at the derivative of fx plus the derivative of negative gx. And the later parts, the derivative of minus gx, according to the constant multiple rule, we have that is actually the negative 1 times the derivative of gx, right? Therefore, we have proved the derivative of hx equals the derivative of fx minus the derivative of gx, which is the difference rule. Okay, now let's have a look at an example. Can you differentiate each of the following functions? Okay, I'll give you 5 minutes to have a look at these 4 questions here. Okay, let's have a look at the solutions of each of the following functions. Question A. Differentiate this function according to the 5 rules we have learned so far. That equals 5 times 6x to the power 5 minus 4 times 3 times x to the power of 2, which can be simplified to 30 times x to the power of 5 minus 12 times x to the power of 2. Any questions? Okay, question B. The derivative of this function. So note here, this function is the sum of 3 parts, right? Therefore, the derivative of this function equals the sum of the 3 derivatives. We can find the derivative of each part respectively and sum them up. Therefore, that equals -3 times 5x to the power 4 plus 8 times 1/2 of x to the power of -1/2 minus derivative of a constant, 0.9. Remember, the derivative of a constant function is always 0. Therefore, that can be simplified to f prime x is -15x to the power of 4 plus 4 over the square root of x. Any questions? Have you done this correctly? The third question. First of all, we can expand this polynomial, right? If you expand this polynomial, you will get gx is actually 2x squared minus x minus 3. Then according to sum rule and the constant multiple rule, the derivative of the sum of 3 parts is the sum of the 3 derivatives. Therefore, the derivative of gx equals 4x minus 1. Okay, last question. Again, first of all, we can simplify this function to convert that to a sum of 2 parts. Then, according to the sum rule, this equals derivative of hx equals the derivative of the first part plus the derivative of the second part, which is -2 minus 6 over x to the power of 4. Any questions? Okay, so basically, according to the sum rule or difference rule, we can find the derivative of a polynomial function. So next, let's have a look at the derivative of a polynomial function. Remember in the previous lesson, we talked about we would like to have the derivative of a elementary function, right? We already have a look at the derivative of a constant function, the derivative of a power function, and today let's have a look at the derivative of a polynomial function like this. So can you find the derivative of a polynomial function, px, which is defined as an times x to the power of n plus an minus 1 times x to the power of n minus 1, all the way up to a1 times x plus a0, where a0, a1, an are constants, and n is a natural number, and n is greater than or equal to 0. Okay, I'll give you 2 minutes to think about this question here. Okay, have you finished? Let's have a look at the solution here. So note here, if you want to find the derivative of px, px is a sum of many parts, right? So according to the sum or difference rule, the derivative of px is the sum of the derivatives of each part. Then the derivative of the first part, according to the constant multiple rule and power rule, equals an times n times x to the power of n minus 1, right? And the second term, derivative of the second term is a minus n minus 1 times n minus 1 times x to the power of n minus 1. And the derivative of the second to the last term equals a1. And the derivative of the last term, which is a constant number, equals 0. Therefore, we have the derivative of px is an times n times x to the power of n minus 1 plus an minus 1 times n minus 1 times x to the power of n minus 2 all the way to a1. Any questions? Therefore, now we already know how we can evaluate the derivative of a polynomial function, right? Do you have any questions? No? Okay, then next let's have a look at another important rule, which is called the product rule. So this rule states that if px is a product of two functions, fx times gx, where fx and gx are differentiable functions, then the derivative of px, p prime x, equals the derivative of the first function, fx, times gx, plus fx times the derivative of gx, g prime x. Or in Leibniz notation, this can also be written as the expression as in the following paragraph. So here, ask yourself a question. Can you prove this product rule? Okay, I'll give you 3 minutes to think about the proof of this rule. Okay, can you prove this? Can you prove this based on what you have learned so far? Okay, any ideas? All right, let's see the proof together. Again, we can use a first principle definition for Px equals Fx times Gx. According to the first principle definition, the derivative of Px is the limit of Px plus h minus Px over h as h approaches 0, right? Then we can insert the expression of Px in there. So that becomes the limit of the product of Fx plus h times Gx plus h minus the product of Fx and Gx over h as h approaches 0, right? So note here, we can insert a term in the numerator position, which is minus Fx plus h times Gx plus Fx plus h times Gx. The reason is to come up with a new derivative. So basically we can combine Fx plus h times Gx plus h minus Fx plus h times Gx over h as h approaches 0. This is the first limit. And according to the limit property, plus another limit of the expression Fx plus h times Gx minus Fx times Gx over h as h approaches 0, right? Then again, according to the limit property, note that in the first term, Fx plus h is a common factor, which can be put in front. So that becomes the limit of Fx plus h times the sum of Gx plus h minus Gx over h as h approaches 0, which eventually becomes the limit of Fx plus h times the limit of Gx plus h minus Gx over h as h approaches 0, right? And the second term is actually according to the definition of derivative, that's actually the derivative of Gx, right? Therefore, the first term is simplified to Fx times the derivative of Gx. Using the similar method, we can convert the second term to Gx times the derivative of Fx. Therefore, we have proved that the derivative of a product of two functions equals the derivative of the first function times the second function plus the first function times the derivative of the second function, which is called the product rule. Okay, next, if you don't have any questions, let's have a look at an example of how we can apply the product rule to solve questions. So use the product rule to differentiate each of the following functions. I'll give you 4 minutes to think about these questions. Okay, you can start now. Okay, let's have a look at the solution here. Okay, actually, there are two ways to find the derivative of the px or y. According to what we have learned so far, these are both polynomial functions. Of course, you can expand them first, and then use a rule to find the derivative of polynomial functions, right? However, this question asks you to specifically use the product rule to find the derivative of both functions. So now let's have a look at how we can do that. Okay, first, note here, px is the product of two functions, right? According to the product rule, the derivative of the product of two functions equals the derivative of the first function times the second function, plus the first function times the derivative of the second function. Then, according to the product rule, the derivative of px equals, let's say here, okay, let's say it here. So the derivative of px is the derivative of fx times gx plus fx times the derivative of gx. Therefore, that equals, first, the derivative of fx is 3, right? Times gx. Gx is x squared plus 1. Plus the derivative of fx. Plus fx. Fx is just 3x minus 5 times the derivative of gx, which is 2x. Therefore, you can expand and simplify, which will give us 9x squared minus 10x plus 3, right? Second question, again, use the same method. The derivative of y with respect to x equals the derivative of first function fx times the second function plus the first function fx times derivative of the second function gx. Therefore, that equals 2 times 1 minus x plus 2x plus 3 times -1. Then expand and simplify. Final answer is -4x minus 1. Any questions? Okay, so similarly, we have the difference rule based on the sum rule. So probably you can imagine the next rule is called the quotient rule, right? Because the quotient operation is the reverse process of product. So quotient rule states that if we have a function q, which is a ratio between fx and gx, of course, fx and gx are differentiable functions, and the derivative of gx, g prime x, is not 0, then qx can be expressed as qx equals the product of fx and gx to the power of -1, right? Then according to the product rule, we have the derivative of qx equals the derivative of the first function times the second function plus the derivative of the second function times the first function, which can be simplified to the form here. The derivative of qx equals the ratio between fx over gx prime, which is also a ratio. The numerator is the derivative of fx times gx minus fx times the derivative of gx over gx squared. This is called the quotient rule, okay? So here, have a look at this quotient rule here. And next, we're going to use the quotient rule to solve some questions. All right, any questions? Okay, now let's have a look at a example. Differentiate qx equals 6x minus 5 over x cubed plus 4. State the domain of qx and derivative of qx. So apparently this is a ratio, right? Which is also called a rational function. So if you want to find the derivative of a ratio between two functions, you can consider using either the product rule or the quotient rule, right? Okay, I'll give you 3 minutes to have a look at this question here. All right, have you finished? Okay, let's have a look at the solution. So according to the quotient rule, we have the derivative of qx equals a ratio. The new numerator is the derivative of the first function, which is the numerator of the original function, times the denominator of the original function, minus the numerator of the original function times the derivative of the denominator of the original function, divided by the denominator squared. And then we can find the derivative of 6x minus 5 and x cubed plus 4 respectively, and put them into the expression, expand, and simplify. Final answer is -12 times x cubed plus 15x squared plus 24 divided by x cubed plus 4 squared. Then let's find the domain of the original function. In the original function, the limitation for our independent variable x is the denominator cannot be 0. Therefore, x can be any real numbers, but cannot be the cubic root of -4. That's the domain for the original function. Then for the derivative function, apparently x cubed plus 4 squared cannot be 0, right? No matter what x is, the denominator is always positive number. Therefore, oh, sorry, my bad. There does have a limitation for the derivative function, right? Again, the denominator cannot be 0. Therefore, x cubed plus 4 cannot be 0. Therefore, the domain of qx, q prime x, is x can be any real number, but x cannot be the cubic root of -4. Any questions? All right, if you have no questions, let's see the last example of today's lesson. Find the equation of a tangent line. Determine the equation of the tangent line to the curve y equals x squared minus 3 over 5x, 5 minus x at x equals 2. Okay, I'll give you a hint. If you want to find the equation of a line, you need a point and the slope, or you need the slope and intercept, or you need two intercepts, right? Or you need at least 2 points on the line. So in the specific question here, because it's a tangent line, we can find its derivative, which is the instantaneous rate of change at this point, which is also slope of this line at this point, right? Find the derivative first. Then use the point slope form to express the equation of this line. Okay, so I'll give you 5 minutes to have a look at this question here. Okay, you can start now. Okay, let's have a look at the solution to this question. Okay, first of all, let's find the derivative of this function first at any point x. According to the quotient rule, the derivative of this function equals x squared minus 3, the derivative of x squared minus 3 times 5 minus x squared minus 3 times derivative of 5 minus x over 5 minus x squared, right? Then we can find the derivative of that two functions first and find the product of these terms, expand and simplify. Therefore, the derivative of y with respect to x equals negative x squared plus 10x minus 3 over 5 minus x squared. Then at x equals 2, we can plug x equals 2 to the derivative function and to the rational function respectively. The derivative of this function at x equals 2 is y prime, which is 13 over 9. That means the slope of the tangent line at point is 13 over 9. And the image of that function at x equals 2 is 1 over 5 minus 2, which is 1 over 3. Therefore, we know this line crosses a point 2, 1/3 with the slope 13 over 9, right? According to the point slope form, this line can be expressed using this form. This is called the point slope form. And usually, okay, point slope form. Usually we'll convert that line to a slope intercept form as final result. This is called the slope intercept form. Okay, so the slope of this line is 13 over 9. The y-intercept of this line is negative 23 over 9. Any questions? Okay, if no questions, let's make a summary of today's lesson. So now let's revisit today's learning goals. So after this lecture, now you should be able to understand common derivative rules, including, so far we have learned the following rules, right? Constant rule, power rule, constant multiple rule, sum rule, difference rule, product rule, and coefficient rule. You can use these rules to determine the derivative of a given function, right? And apply the common derivative rules to solve related problems. Then differentiate a polynomial function. You can use these rules to differentiate polynomial function. And then differentiate a rational function. So here we have learned how we can differentiate a constant function, a power function, a polynomial function, and a rational function, right? So in chapter 4, we'll learn how we can differentiate trigonometric function, an exponential function, and logarithmic function. We'll talk about that in chapter 4, okay? All right, today we have learned some common derivative rules. These are very simple rules. In tomorrow's lesson, we'll have a look at more complex rules, including the chain rule and explicit differentiation. Okay. So this is the end of today's lesson. Remember to complete today's homework and submit them onto Google Classroom on time.